When you think about it, our universe is, well, it's pretty chaotic, right? But there's this one thing, this one speed, that's like the ultimate rule book for everything. It's the cosmic speed limit. It dictates how fast we can communicate, how energy and mass are connected, and even how we perceive time. And yep, you guessed it, we're talking about the speed of light.
Okay, just look at that number for a second. 299,792,458 meters per second. It's just a massive number. But here's the crazy part. That's not an estimate. It's not something we're still trying to get more accurate. Since 1983, that number is the definition. It's exact. We actually changed the definition of a meter just to lock this speed in place. How wild is that?
And that's because, well, it's not just a record for the fastest thing we've found. It's a law, a hard and fast rule of the universe. This is the absolute maximum speed that anything, any information, any signal, anything can travel. If you have mass, you can't reach it. And if you don't have mass, like a photon of light, you have no choice but to travel at exactly this speed in a vacuum. It is a totally fundamental, unbreakable law.
All right, so we've got this massive number, but what does it actually feel like? How fast is fast? It's kind of hard to get your head around something that big. So let's try to bring it down to Earth a bit, and then we'll zoom back out to see what it means on a cosmic scale.
Okay, check this out. In the time it takes you to blink, a beam of light could zip around the entire Earth more than 7 times. Just gone. It takes light about 1.3 seconds to get from the moon to us. That sunlight you're feeling on your skin? Yeah, that left the sun about 8.5 minutes ago. But then you look at bigger distances and the perspective totally flips. To get from one side of our own Milky Way galaxy to the other, light needs almost 90,000 years. So you see, it's this incredible paradox. It's unbelievably fast for us, but on the scale of the universe, it's almost a crawl.
So who figured all this out? Well, the guy who really understood just how deep this rabbit hole goes was, no surprise, Albert Einstein. He was the one who realized the speed, which we call c, wasn't just some random property of light. Nope, it's something much, much bigger. It's a core rule baked into the fabric of space-time itself. So the big thing to remember here is that c is the universal speed limit, period. It's not just for light, it's for any massless particle or wave. That includes gravitational waves. Think about this for a second. If the sun just vanished, right now, we wouldn't know for 8.3 minutes. We'd still see it shining, and we'd still feel its gravity holding us in orbit for that whole time. The darkness and the gravitational shock wave would arrive at the exact same moment because they both travel at c. Now get ready, because this is where things get really weird and break your brain a little. Einstein's big idea in 1905 was this. It doesn't matter how fast you're going. It doesn't matter how fast the thing shining the light is going. If you measure the speed of that light, you will always get the exact same number, c. Always. So if you're standing on the ground with a flashlight, or you're in a spaceship going half the speed of light with a flashlight, the light from your flashlight moves away from you at the exact same speed. Our normal logic about adding speeds just completely falls apart. So if the speed of light is always the same for everyone, no matter what, how is that possible? Something's got to give, right? Our everyday experience says speeds should add up. Well, the thing that gives is, believe it or not, space and time. To make sure everyone agrees on the speed of light, the universe literally bends and stretches space and time in some of the weirdest ways imaginable. So how does it do that? Okay, imagine you fly past me in a super fast rocket. From my perspective, I would actually see the clock inside your rocket ticking slower than mine. That's called time dilation. Not only that, I'd see your rocket as being literally squished, shorter in the direction it's moving. That's length contraction. And it gets even stranger. If I see 2 lightning bolts strike at the exact same time, you, whizzing by in your rocket, might see one happen before the other. The very idea of at the same time depends on how you're moving. All of this weirdness, this flexibility of space and time, happens for one reason: to keep the speed of light constant for both of us. And all of this leads us to maybe the most famous equation in all of science: E equals mc squared. What this is really telling us is that mass and energy are 2 sides of the same coin. They're interchangeable. And that c squared in the middle, that's just the conversion rate. And since c is a gigantic number, squaring it makes it astronomical. It means that a tiny, tiny amount of mass is actually a huge amount of bundled up energy just waiting to be released. Okay, so a logical question pops up, right? If it's just a speed, why can't we break it? Why can't we just build a big enough rocket and keep pushing until we get there, or even go faster? What's the roadblock?
The answer is energy. As you try to push something with mass faster and faster, it gets harder and harder to speed it up. The energy you need to get just a little bit faster starts to skyrocket. As you get really, really close to the speed of light, the energy required to go any faster approaches infinity. And since, there isn't an infinite amount of energy available in the universe, you can never quite make that final push. The speed of light is the ultimate finish line that nothing with mass can ever cross.
All right, so this all sounds a little out there, right? Like abstract physics that doesn't really matter. But trust me, the speed of light and all its weird consequences have a direct impact on your life, probably in ways you've never even thought about.
Take the device you're watching this on right now, a computer, a phone, whatever. Its maximum speed is literally limited by the speed of light. See, in a 1 gigahertz processor, an electrical signal has 1 billionth of a second to get its job done. In that tiny sliver of time, it can only travel about 30 centimeters, or about a foot. That's it. This is why engineers are obsessed with making chips smaller and packing things closer together. It's a race against C.
Or how about GPS? This is probably the best everyday example of relativity. Those GPS satellites are orbiting Earth super fast, and they're also in a slightly weaker gravitational field than we are. Both of these things actually change the rate at which their internal clocks tick compared to ours down here. It's a tiny, tiny difference, but if the engineers didn't correct for it using Einstein's equations, your GPS location would drift off by kilometers every single day. So yeah, that weird physics is the reason your phone knows where you are.
But it's not just about technology. The speed of light gives us something even more profound. When you look up at the stars, you're not seeing them as they are right now. You're actually looking into the past. Because those distances are so huge, the light has taken a long, long time to travel from the star to your eye.
For instance, the light from our closest stellar neighbor, Proxima Centauri, it's over 4 years old by the time it gets here. When you look at the Andromeda Galaxy, our closest big galactic neighbor, you're seeing light that started its journey 2.5 million years ago. And when we point something like the Hubble Space Telescope way out into deep space, we're seeing galaxies whose light has been traveling for up to 13 billion years. We're literally seeing the universe when it was just a toddler. Every telescope is, in a very real sense, a time machine.
We didn't always know this stuff. For a really long time, people thought the speed of light might be infinite, that it was just instantaneous. Figuring out that it had a speed and then actually measuring it is a pretty cool story of scientific detective work. It started back in 1676 with a guy named Ole Romer. He was watching the moons of Jupiter and noticed their eclipses seemed to be a little early or a little late, depending on where Earth was. He realized it was because the light had a longer or shorter distance to travel, the first real proof it had a finite speed. Then, in the 1800s, James Clerk Maxwell did some math on electricity and magnetism and, poof, out popped a number for the speed of an electromagnetic wave, and it was a perfect match for the speed of light. Of course, the real game changer was Einstein in 1905, who said this wasn't just a speed, it was a fundamental constant of nature. And finally, in 1983, we just stopped measuring it. We decided it was so fundamental that we fixed its value, and now we use it to define what a meter is. That's how important it is.
So when you boil it all down, C is about so much more than just how fast light travels. It's the speed of cause and effect. It's the universe's way of making sure that you can't get a response before you've sent the signal. It's the ultimate speed limit for information, the very rhythm that the cosmos runs on.
And that brings us to one last kind of mind-blowing thought. The universe is expanding, and because of that, there are galaxies out there that are so far away, the space between us and them is stretching faster than light can even travel. Think about that. Nothing is breaking the speed limit through space, but space itself is carrying them away from us too fast. This means their light will never reach us, ever. They are gone from our view forever, beyond a cosmic horizon we can never peer past. So it really makes you think, if C is the ultimate gatekeeper of information, how much of the universe is out there that we can just never know about?